Welcome to Math 31. This is a continuation of the lesson on the first lesson on related rates. So all the questions that I do will be coming from that first document for the notes. And these questions are going to involve three common applications: volume questions, shadow questions, and ladder questions. So to begin, take a look at a water tank that has the shape of an inverted circular cone with base radius 2 meters and a height of 4. And the water is being pumped into the tank at this rate, 2 cubic meters per minute. We want to get the rate at which the water level is rising when the water is exactly 3 meters deep. So these lend themselves to related rates, these types of problems, because you can get a sense when you look at this that if water was being pumped in at a fixed rate, which makes a type of sense, there's a certain amount of water being put in there, that's not going to change. But the height and the radius are going to be changing simply because of the shape of it. So it's a dynamic system, and if you try to Armstrong your way through something like this, it would overwhelm your cognitive abilities. So we can use calculus to solve these ones, related rates specifically, and they work very well. Now, first to begin, I guess, we should be aware that the formula for volume of a cone is 1/3 pi r squared h. Formula will usually be given to you, and if you were to substitute a specific h value into that, or a specific r value, all you would get would be the volume at that particular time. And that's not what we want. In fact, as you read on the question, you'll see that we want to find the rate at which the water level is rising when the water is 3 meters deep. So we want, ultimately, dH dt. Specifically, at h is equal to 3. So when the height is 3 meters exactly. Now, a couple of things to be aware of. When you look at that original relationship between volume r and h, it has 3 variables. Now that shouldn't be a big problem if you consider that the previous question we did on this lesson gave us an area problem with base and height, and we were able to use the product rule to break it down. Now that worked out, and it might work in this case with r and h. You could break that down, but if possible, if you can express one variable in terms of the other, then you can simplify it. And that's normally what you try to do with these questions. The one before was actually a bit of an oddball one. And because this question is asking for h values and giving you h is equal to 3, the trick will be to express r, the radius, in terms of h. Now, how we're going to do that is based on this original measurement of 2 by 4. You see what happens as the water level rises, we get a series of excuse that last scratch there, we get a series of similar triangles. So the ratio of radius to height is always going to be 2 to 4, always. So it doesn't matter where you it doesn't matter where you are within that triangle. So by multiplying this one out, 4r is equal to 2h, and then isolated the r by dividing by 4, we'll get radius is equal to 1/2 h. So we wanted to do that because we can substitute this r back into the equation there, and express the whole thing in terms of h. And I chose r in terms of h because everything was given to us. The question was asked, and h equal 3. So it makes sense to do that. Otherwise, we'd be solving it with a radius, and we wouldn't be getting the same information. So now, v is equal to 1 over 3 pi. Instead of r, we get 1 over 2 h all squared times h. So v is equal to 1 over 3 pi times 1/4 h squared times h, so that's h to the 3. So v is equal to 1 over 12 pi h 3. So that's where we want it. And we now differentiate with respect to time. So I'm going to get a little bit more space on the next screen. So dv dt is equal to 1 over 12 times 3, 3 over 12, which reduces down to 1 over 4 pi h squared, and then dh dt. So this is not that bad of an equation. And we do want to get dh dt. That's the variable in question. So what I like to do with these is take stock of what I have and what I'm asked for. Rather than listing all the information at the start of the question, which is a very conventional way to do word problems, I differentiate this first. I always identify what I'm looking for, so I know that. And I differentiate, and then I go say, well, okay, do I have this? Can I get this? Sort of thing. And we do have h is equal to 3, and dv dt is water is being pumped in at 2 cubic meters per minute, so dv dt is in fact equal to 2. So that's the number we're looking for. So 2 is equal to 1 over 4 pi h is equal to 3 squared dh dt. And I know you're thinking, well, shouldn't we manipulate first? And of course you can, but this is a fairly easy one to deal with. So I'm not going to do it till, I'm not going to bother in this case. So I'm going to multiply by 4, giving me 8, and then I'll divide by 3 squared, which is 9 pi. So dh dt is equal to 8 over 9 pi. And I note that the question was asking for an exact value, so I'll say that the height or the water level is rising at 8 over 9 pi. In this case, we're at meters per minute. So fairly typical, fairly routine problem. Now the next one is very similar. I'm not going to bother going through this one. I'm going to, just because it's so similar, you probably get bored anyways. But we'll give you the answer. So I'd advise you, I'd recommend that you try this one. The answer to the nearest 1,000th, 3 decimal places, would be negative 0.497. Units would be centimeters per second. And the other thing is that we want to be aware of is that water is drained from this filter at this rate. So dV dt, the volume is decreasing, and that would be negative 25. So don't forget the sign. But the rest of it works just like the earlier question did. So if you run into problems with that, please contact me and I'll see what I can do. And then I'm going to move on to the next question, the shadow problem. And you get lots of shadow questions, well, in this sort of level of calculus. I don't know if these are the most practical ones you're going to ever get, but they're interesting problems. we have a man walking away from this light post at this specific rate, and we're asked to find at what rate is the length of his shadow changing. Now the setup for the diagram is critical because it's easy to forget what's going on with this. There's a light, it looks like the sun, at the top of this post, and here's this guy. It looks like he's just walking away from graduation. I didn't catch that earlier. Away from the light post, and his shadow, which is going to be on the ground, is changing. Now, this diagram is a little misleading, not just because we got a guy walking away from grad, but through no real fault of the designer, we can't see what's going on. This triangle is actually expanding as he walks. So as he walks further and further away from this light, it's going to change the size of the shadow on the ground. So the triangle itself, the dimensions of it, would be changing. And the method that we usually use for shadow type problems is similar triangles. We really were using similar triangles on the previous one in order to express R in terms of H. But here we use them to actually create the equation. Because no matter what is going on, if you treated that guy as just the side of a triangle, no matter what he's doing, no matter how far he walks, you are creating a triangle, two triangles that will be perfectly similar. The angles will be the same. You have the big one, and you'll have the little one, which I've drawn in the exact opposite way. So for the big one, you're going to have 5.55 meters, and then for the small one, you're going to have his height, which is 1.85 meters. And if we treat the length of the shadow, give it the variable s, whichever you want to call it. I'll just give it s with a hook. And then treat the distance that he's covered, the horizontal distance as x. We're able to put in variables for these two similar triangles. Because the 5.55 triangle, the horizontal side will be x plus s. Whereas the 1.85 one is s, like that. And similar triangles, of course, have the property that 5.55, the ratios of the sides are going to always be the same. So 5.55 over x plus s will be equal to 1.85 over s. And if we look at what's going on with this, we have the two variables, x and s, but what we're asked to find, ultimately, is the rate that the length of the shadow is changing. So we want ds dt. And if we multiply out these two fractions, this proportion, we'll get 5.55 s is equal to 1.85 multiplied by x plus s. And then we distribute that 1.85 in, so 5.55 s is equal to 1.85 x plus 1.85 s. And bring the s's together. And if you do so, subtract them over to, say, the left side. 5.55 minus 1.85 will give you 3.7. So 3.7 s is equal to 1.85x. We're actually good enough now, but I'm going to go further. I'm going to isolate the s so I don't have to do anything fancy with this. 1.85 divided by 3.7 is actually equal to 1/2 x. 0.5. And now when we differentiate with respect to time, as always, we'll get ds over dt is equal to, well, 1/2 times dx dt. And we pause and see if we have all the information we need. This turned out to be a very simple equation, of course. There's just two variables, ds dt and dx dt. And looking at the question, we can see that he's walking away at 2.15 meters per second. So dx dt we have. Now I'm going to bring up a new screen to get some space to work this one out. But 2.15 is the dx dt. So ds dt is equal to, I'll write that as 0.5 multiplied by 2.15, which was our dx dt, and we get ds dt is equal to 1.075. And I guess the units in this case are meters per second. So the shadow is increasing at a rate of 1.075 meters per second. Something that's of interest in this question, if you thought about it, is that the rate is actually constant. Like the previous question, the volume ones, it's draining as the water is draining or is being pumped in. The dHdt would be changing at every h value or every t value. Here, not so. And you may have noticed that from the question that it never asked what rate is it changing at specifically h or s equal to 4 meters or something like that. So that means that it's actually at a constant rate. And we can see that with the equation too, that when we differentiated, there was no x or s in the equation. We just had ds dt and dx dt. So that's interesting a little bit. Let's do one more, a ladder question, which really does illustrate another very common type of problem. Hopefully not a real-life application that you experience too often, but this ladder is leaning against a vertical wall. And the bottom of the ladder is slipping away at a specific rate. And we want to figure out, well, how fast is the top of the ladder moving down the wall when the bottom is exactly 5 feet from the base? So there's a rough diagram. Now, these ones are useful because we see versions of them all over the place. This is actually a fairly simple one compared to some of the ones we'll look at tomorrow. But the nature of this question is that we end up using Pythagoras' theorem. It's not a set of similar triangles because we just have the one triangle, but we do have a changing triangle except for the hypotenuse. The hypotenuse would be the length of the ladder, and it is constant. So we're going to build it right into the equation. And I'm going to call this side y, the vertical side, and I'll call the x horizontal side. And because the tip at the end of the ladder is going down, that's going to be decreasing, and then x is going to be increasing. So don't treat this as though it's on a coordinate grid where x is going in the negative direction. What's actually happening is the distance, because the base of it is slipping away, the distance from the base of the ladder to the base of the wall is going to be increasing. Now we want ultimately to find how fast is the top of the ladder moving down the wall. So we want dy dt. Moreover, based on this question, we would assume that dy dt is going to be a negative value. It is decreasing. So we should get that in our answer. and we work with this formula. X squared plus y squared is equal to the hypotenuse squared, which is 13 squared. Reminder, this question is saying we want our answer when the bottom of the ladder is 5 feet from the base, so when x is 5. But remember, you don't substitute that into the original. I mean, if you did, all you'd be getting would be the y value when x is 5. Now, that might be useful in this question, but it isn't the answer for this. So you need to remember that the first equation is always giving you information on how long x and y are. The second one, the derivative, is going to be giving you the rate of change equation. So I'm going to add to this, though. We want dy dt at x equal 5. So when we differentiate, we get 2x with respect to time, 2x dx dt, so we must have that, it's implicit differentiation, plus 2y dy dt is equal to the derivative of 13 squared is 0. I'm going to divide out by 2. So x dx dt plus y dy dt is equal to 0. I'm going to now look at this question and the equation and see what I've got and what I'm missing, if anything. Dy dt is the variable we're looking for. Dx dt, well, it's slipping down, or it's slipping away at 2 feet per second, so dx dt is equal to 2, positive 2 feet per second. I'm not going to substitute the units in, but we have it. This is all happening when x is equal to 5. So the only question is why. Now, of course, a few minutes ago I said you do not substitute into the original equation, but you do if you're trying to find out what y is equal to when x is equal to a specific number. So it just doesn't get us our answer. So to find y at x equal 5, so 5 squared plus y squared is equal to 13 squared. So y squared is equal to 13 squared minus 5 squared. So y squared is equal to 169 minus 25, so that's 144. So y is equal to plus or minus 12. And really only the positive 12, because the distance is going to be measured in a positive unit. So we're good to go. Substitute everything in. X is equal to 5. Dx dt is equal to 2. Y is equal to 12 multiplied by dy dt. This is equal to 0. So bring the 10 over. So 12 dy dt is equal to negative 10. So now when you divide, I'll just do this to the side, and then I'll get a little more space. Divide by 12, you'll get negative 5 over 6 when you reduce that fraction. It is negative as we wanted it to be, as we expected it would be. So we can wrap this one up by saying that the ladder is slipping down the wall at 5 over 6 feet per second. So because I have the direction indicated in the answer, I don't need to put the negative. It would have been correct just to say that it's the answer is negative 5 over 6 feet per second as well. But if you do write a sentence like in a physics class, if you give the direction, then you don't need to put the sign for it. So that's going to take care of this. There will be another series of questions on related rates where we look at different applications, travel, and a few other things like that. Thank you for your time.